Welcome back to the Chapter 9 video lecture for Chemistry 1510. At this time, we're about halfway through Chapter 9, and you should have spent some time in class practicing Lewis structures. And so today, we're going to pick up with Lewis structures, but we're not going to practice any right here because you've already had an opportunity to do that. Instead, we're going to start going deeper into Lewis structures. And what I mean by that is we're going to now utilize those Lewis structures in future types of problems. So as we start moving into the new information, we have to discuss what's happening in chemical bonding. So in chemical bonding, there's two types of bonds. There are covalent bonds, and your covalent bonds are the ones that we're drawing in Lewis structures. These are where electrons are shared between the atoms. And the other kind of bonds are the ionic bonds, where electrons are transferred. Now, inside of ionic and covalent bonds, people think that it's either one or the other. But the thing is bonding is really a continuum. So I'm going to draw a little line here to start to illustrate bonding as a continuum. And there's really kind of three sections in bonding. There are nonpolar covalent, and then there are polar covalent bonds, and then we get into ionic. So in the chemistry world, what ends up happening is usually bonds are classified as one of these three types. And the way that you figure out what the bond is or should be classified in is by using the difference in electronegativity. So delta, the triangle I just drew, is mass symbol for difference, and En is electronegativity. So if we're looking at a difference in electronegativity of 0 to 0.4, that is going to be classified as a nonpolar covalent. When you hit 0.5, that is a polar covalent. And then this last number isn't widely agreed upon of where the cutoff is between polar covalent and ionic. Some textbooks say 1.7, some say 1.9, some say 2.0. So I guess let's split the difference and call it 1.9, and that way we'll start ionics at 2.0. So what we do to figure out if a bond is covalent or polar covalent or ionic is we look at the atoms that are involved in the bond, we find their electronegativity values on the periodic table, and then we subtract. So for example, if we just draw a quick example right here, and we're looking at something maybe like a CO bond, the electronegativity value for carbon is 2.5. The electronegativity value for oxygen is 3.5. When you subtract them, you're making sure that you're always getting a positive number, so you're always subtracting the smaller quantity from the larger quantity. And so we're seeing the difference in electronegativity as 1.0. And so that's going to be classified as a polar covalent bond. So let's talk about what it means to be polar covalent. So if a bond is polar covalent, it means that those electrons in the bond are being shared unequally. So in this bond, the oxygen has the higher electronegativity value. Electronegativity is a measure of how badly the atom wants the electrons in the bond. And so what will happen is in this bond, the oxygen will pull the electrons toward itself, leaving a little bit of a positive charge on the carbon. And so the way that you'll see this written is people will write a partial positive, which I know that doesn't look very nice. That's supposed to be my lowercase delta, which is kind of like an S, and a partial negative. So the more electronegative the atom, the more it wants that electron density in the bond on its side of the bond. And so they're not sharing equally. So a nonpolar covalent bond, these would be equal sharing of electrons. A polar covalent bond is still sharing of electrons, but unequal. And then an ionic bond is a complete transfer of the electrons to form ions, which are then electrostatically attracted to one another. So if we think about equal sharing versus unequal sharing, equal sharing maybe in real life would be two children who say, all right, I'm going to set a timer for 5 minutes and I'm going to play with the iPad for 5 minutes, and then when it beeps, you can play with it for 5 minutes. So obviously that's not normal, not in real life, and also not in the chemistry world. So a lot of our bonds are going to be polar covalent, and they are going to be having electrons in those bonds that are unequally shared. And as we build on this topic for the remainder of the semester, what we're going to find is that these polar covalent bonds lead to other situations that we see in real life, like why water has such a high boiling point. So let's keep talking about bonds. And we already said that ionic bonds are formed between ions where electrons are transferred. Whereas in covalent bonds, we're seeing the electrons be shared. In covalent bonds, because the electrons are shared, what's happening is we have orbitals that are overlapping. So let's pretend we're looking at the hydrogen-hydrogen bond. Each hydrogen has a 1s orbital, and here I have a 1s orbital. When these two 1s orbitals overlap, that sharing is the bond. And so what we can then see is if the center is the nucleus there, and the center of the nucleus, or the center of the atom, the nucleus is there, then what we can do is we can measure a bond distance, so a distance between the nuclei. So that distance is called the bond length. And this is actually something that we can measure. And then we can also measure something called the bond energy. And so right now, what we want to know is that there is a trend in bond energy and bond length. If we look at a single to a double to a triple bond, and we're increasing the number of bonds between two atoms, what happens to the bond energy is going this way, the bond energy increases. And the bond energy is usually defined as how much energy it takes to break that bond. And then as we go from single to double to triple, the bond length, so the distance between the nuclei, decreases. So triple bonds are shorter than single bonds. So the question is then, why are we even having this conversation? Who cares about the relative energy and length of these bonds? And the reason we're having this conversation is because when we go to the next page and we look at a Lewis structure, I'm going to draw the Lewis structure for H2SO4. So when you draw a Lewis structure for an oxoacid, which is what H2SO4 is classified as, remember that the hydrogens in the Lewis structure are always connected to the oxygens. And when you're looking at it saying, oh, but I wanted to draw, the other hydrogen down here, that doesn't matter. Put the other hydrogen wherever it makes you feel happy. We'll worry about shapes and whatnot later when the time comes. So here is the Lewis structure for H2SO4 that you would have drawn after doing the initial part of chapter 9. So in our Lewis structure, let's look at those SO bonds. Do they appear to be the same? And to me, the answer is yes, right? They are all single bonds. And you might have said, no, two of them have a hydrogen on the other side and two of them don't. And I'm not concerned with what's on the other side. We're looking at what the SO bonds are. So the thing is that we can actually measure bond length and bond strength. So when we measure bond length, it shows that the SO bonds with no hydrogen attached are shorter than the ones with the hydrogen attached, which is wild because if you were thinking, oh, those bonds are different. Well, what the data is showing is that the SO bonds are actually a completely different bond. They're not single bonds like these ones are, right? They're saying that the bonds that I'm highlighting in yellow are shorter than the bonds that I'm highlighting in pink. And so now we have a problem. Our problem is that our Lewis structure and our data don't match. And so what we do is we start to then rethink our Lewis structures and say, how do I change our Lewis structure so that it matches the data? And so what I'm going to show you is how to draw a structure that violates the octet rule, but then fits with the experimental data. And so I'm going to change this around a little bit to something that violates the octet rule. And I'm going to take one of the pairs on the oxygen that doesn't have a hydrogen attached, and I'm going to just swing it around. I'm going to draw it as a double bond. And then I'm going to take one of these pairs, it doesn't matter which one, and swing it around so that it makes a double bond. And so remember that when we drew Lewis structures in class last, we did say that certain elements can expand the octet, so they can have more than 8. And indeed, sulfur is one of those because it's in the 3rd period. So we said anything in the 3rd, 4th, 5th, 6th, 7th period, any of those elements can all expand their octet. And so now we look at this and you're thinking, how in the world am I to know that on the exam I need to draw the boxed structure versus the one we initially drew? And that is where the idea of formal charge comes in. So if we look at formal charge is a comparison between how many electrons the atom typically wants, so it's valence electrons, and how many electrons the atom owns in that structure that you're considering. So here I've highlighted my valence electrons, part of that equation, in yellow. Here my atom ownership, right, is in pink. So how many electrons that atom actually feels like it owns. And the difference between that is the formal charge. So if we go back to our previous example and we start calculating formal charge, let's start on this structure. Before we start, let me call this oxygen A and this oxygen B so that we can tell the difference. So if we look at oxygen A, the formal charge for oxygen A is going to be 6 valence electrons, because oxygen has 6, minus the number of lone electrons. So you're not counting lone pairs, you're counting singular electrons, right? So 1, 2, 3, 4, 5, 6. And there's one bond that oxygen is involved in. So that oxygen has a -1 formal charge. And what we'll do is we'll put the negative by that oxygen, and sometimes people will put a little baby brackets around it. Sometimes people will draw a circle around it. So then let's also do the formal charge on sulfur. So we got the formal charge on sulfur. Formal charge on sulfur. Sulfur also has 6 valence electrons. In this structure, there are no lone electrons on the sulfur, and there are 4 bonds. Oops, wait, I just saw a mistake. This is supposed to be a plus sign. I apologize. And so now your sulfur has a positive 2. So I've got a negative on oxygen A, and if you'll notice, this oxygen at the bottom also has the same pattern as oxygen A with 1 bond and 3 lone pairs, so it's also going to have a negative charge. The sulfur we said was a plus 2. And then if you go through and you take a moment to calculate the formal charge for the other atoms, what you'll find is that this one has a formal charge of 0 and 0 and 0 and 0. And typically we do not write the 0 formal charges next to atoms because it ends up getting really messy in that structure. So now let's look at the other structure, the one that's in the box. And we'll still call this oxygen A, and this one will be oxygen B. So now if we calculate the formal charge of oxygen A, oxygen still has 6 valence electrons. There are 4 individual electrons touching that oxygen and 2 bonds. So it has a formal charge of 0 now. We look at the formal charge of sulfur. Sulfur still has 6 valence electrons. That's coming from the periodic table. And no singular electrons around it, but 6 bonds. So a 0 formal charge. So look at this. Now what we've done is we've drawn a structure that violates the octet rule, right? This one right here. And it has 0 formal charge across the atoms that before had a plus 2 and a minus 1 formal charge. So initially we had 3 atoms with a non-zero formal charge, and now we have everything in this box structure has a non-zero formal charge. No, wait, did I say that right? Has a 0 formal charge. So this is what we're looking for. When we are done drawing our structure, we're going to assess the formal charge of, excuse me, of that central atom. And if the central atom is not a 0 formal charge, it usually means that we can adjust things. And of course, this adjustment can only happen if the element has, or the central atom can expand the octet. If the central atom cannot expand the octet, then we can't do much. It's just going to have to sit with that formal charge that's a little bit undesirable. So let's look at maybe 2 more examples. I'm just going to keep scrolling here. And why don't you go ahead, take a quick moment to pause and write in these structures that I've written here that are not drawn in your notes. So take a quick moment to pause and then come right back. All right, so my assumption is that you've had a moment to draw these in, and what I want to do is show you some pitfalls, because students so often end up with the idea of formal charge and they just latch onto it, and then everything really becomes a formal charge question to them. And so if we look at this first question of what's the best Lewis structure for carbon monoxide, what students will do is they'll go through and they'll calculate the formal charges. And if you want to pause for a moment and calculate the formal charges on the carbon and the oxygen in both these structures, please do. Otherwise, I'm going to tell you what they are. So here I go. That should have a 0 formal charge. Oh, wait, did I do that right? 1, 2, 3, 4. No, it doesn't have a 0 formal charge. I wanted to draw one with a 0 formal charge. Well, maybe this question stinks. That has a 0 formal charge. 1, 2, 3, 4, 5, 6. Huh. I'm going to have to change this question. Go away. Let's change the question to, can you draw a better Lewis structure than the one I've drawn for carbon dioxide? I'm sorry, I said carbon dioxide and I meant carbon monoxide. And so what you will do is you'll look at this and you'll say, okay, this carbon has a a -1 formal charge. And this oxygen has a +1 formal charge. And so you look at it and you say, well, but I just learned that having 0 formal charges is better, so I'm going to do some stuff. And in this case, you can't do anything. Because as you noticed, if you go back and unpair, this one is bad for 2 reasons. One, because the formal charge is still not great, but also because I had too many electrons here. It's not even a valid structure to begin with. Whereas over on this example, I have a valid structure to begin with because I've drawn a total of 10 valence electrons and everything has an octet. But students will see this +1 and -1 and say, oh, well, that's not good. And then they do some very unusual things. And I'm not even sure I want to tell you what the unusual things are, so I'll just give you a hint. There's no such thing as a quadruple bond. You end at a triple bond. So let's go to a question that I know looks good. And I want you to look at these structures and tell me which one that you think is best based upon the formal charge. And so you can pause here right now if you would like and calculate some formal charges. Otherwise, I'm going to give you formal charges and then you can pause after that to think. So this one is a negative, that's a 0, that's a 0, that's a 0, that's a +1, negative, negative, 1, 2, 3, 4, 5, 0, 0, 0. And if you're thinking, dang, she's doing this fast, once you get to organic chemistry, you'll do it this fast. 0, 0, 1, 2, 3, 4, 5, 0. All right, so pause for a moment if you need to and actually think about the question and what it's asking, right? It's asking which one of these is the best structure. So most of the time, students will choose letter C. And they will choose letter C because they see that everything has a 0 formal charge. So this question is in here because of this common pitfall. What you want to remember is that before formal charge kicks in, you must draw, the number one most important thing is to draw a valid Lewis structure. Then number 2 is to consider formal charge. So let's go and look at this Lewis structure for nitric acid and say, is this valid? And look at that nitrogen and count your octet. Does it have an octet? That nitrogen? Hopefully you're saying no, because that nitrogen has 10 electrons around it. And so that is not a valid Lewis structure. Then you might look at B and A and say, well, they each have some formal charge there. So how do I tell which one is okay? And if you count the number of electrons for structure B, what you're going to find is that you have 2 too many electrons that you're not allowed to have. And so really structure A is the correct answer. This is the best Lewis structure because it's a valid Lewis structure. We've drawn the correct total number of electrons. Every atom has an octet, and then we consider formal charge. There's no way to lessen this formal charge. It's not possible. So sometimes you just have to deal with a non-zero formal charge on the central atom, and that's okay. So I'm going to let you try this one if you care to. Otherwise, I'm going to keep going for the sake of time. So sometimes at this point, when we start drawing things, let's see. This structure. Students will ask me, does it matter if I draw it the way that you drew it, or should I draw it this way? That's a really, really great question. And usually when they ask me, it's when they first learn Lewis structures, and the answer is do whatever you want. But now that we are further into Lewis structures, we're going to start talking about something called resonance structures. Just to preemptively warn you, resonance structures can be mind-boggling. So here's the thing. When we look at these two structures up here, no matter which one you're looking at, you have one double bond. Can I tell you a secret? I don't think I know how to spell double. Are there two B's? Oh, goodness. You'll tell me in class. And one single bond. So when we look at either of these structures, there's one double bond between carbon and oxygen and one single bond between carbon and oxygen. But if we go and we look at the experimental data says that the carbon-oxygen bonds have the same energy and the same length. And so what that means is our Lewis structures have failed us. And we need to add to our Lewis structure theory. And the way to do this is with resonance structures. And so really what's happening is we don't draw just one of these structures when we're drawing resonance structures. We draw both, and then we put a double-headed arrow between the structures. And a lot of the times resonance structures are made up of ions, and so we draw them in brackets like this. And so we put the resonance structures in brackets with a double-headed arrow, and that double-headed arrow means that these are resonance structures. And so what is a resonance structure? Well, usually a resonance structure is not really a singular thing, it's a set. And in this set of resonance structures, what we're saying is we want you to average these two structures. And you're going to usually do that in your head, but we can also do that on paper. I think I have a section down here when we look at the resonance hybrid. So before we had the carbon with the bond to hydrogen, we definitely had a single bond to each oxygen. And then what we did was sometimes we had a double bond here, and in the other structure, we had a double bond here. But if we average this, we really don't have a complete double bond, right? We have a double bond in one scenario and then a double bond in a different location in the other scenario. So really what's happening is that double bond, those electrons, are being shared partially between that carbon and oxygen and partially between this carbon and oxygen. So this is a resonance hybrid. One of the things that you're going to notice about the resonance hybrid is that it has dashed bonds. This is describing a partial bond. And the other thing is it leaves off lone pairs. Right, so usually there's dots around these oxygens, and we don't really draw those in the resonance hybrid because it gets really confusing very, very quickly. So essentially, we have a 1.5 bond is what we're trying to say. That neither, if we scroll up, neither of these structures actually exist. Right? Neither of those exist. What exists is an average between them. Now, let's real quick add one more idea to this. And that is that now that we've calculated formal charge, we can put a negative formal charge on this oxygen here and a negative formal charge on that oxygen there, because look at our formate anion has a negative formal charge overall. And so if we come back to our resonance hybrid and we want to include that formal charge, what we did was we had a negative charge on this oxygen in one structure, and we had a negative charge on this oxygen in the other structure. And so that negative charge is being distributed between two atoms, so each oxygen feels like it has a negative 1/2. All right, we are going to practice this a boatload more in class, and so for the sake of keeping a video on the shorter side of things, I will leave this part for you to practice if you like, and this one as well, and I will show you more examples during class. So, why do we care about resonance structures? Because having resonance makes an overall more stable situation. So it lowers this energy. And for those of you who end up taking more chemistry, this idea of resonance stability is going to be huge in organic chemistry. Like really big. Like there's a whole chapter on just drawing resonance structures, and then we use them literally for the entire class. They never go away. And there's going to be a whole bunch of rules on how to draw them, and right now all you're doing, your only rule is switching the location of the double bond, and they're going to get so expanded on in organic chemistry, and it's beautiful and it's wonderful, and hopefully you love it. So let's end with some stuff about polarity of bonds. So we've already talked about electronegativity, about how an atom can attract electrons to itself. We saw on the periodic table that we had a general trend that going toward fluorine, we increased electronegativity, and in general, the noble gases were ignored, and they don't really have electronegativity values. And that's not completely true. I mean, krypton and xenon and radon technically do have electronegativity values, but a long time ago, they didn't think they did. And so when we look at the groups on the periodic table, right, halogens have a high electronegativity, and they are going to form that -1. Oxygens will form the -2. Alkali metals, which has a very low electronegativity, will form a +1. Alkaline earth will form a +2. We've already talked about how bonding is a continuum, and so I don't feel like I need to repeat that. And this is where I want to get to. I want to get to how the three elements on the periodic table with the highest electronegativity are oxygen, nitrogen, and fluorine. So when we start to look at how we're going to use electronegativities in the future, these atoms are going to be a big deal. And so what we want to be able to do is apply the knowledge from the very beginning of the chapter where we talked about how bonding was a continuum. And what I want to do is give you a moment to look up the electronegativity values for hydrogen and iodine. And there's a table down here, so you can look at that table. And hydrogen is a 2.1, iodine is a 2.5. So even though we would call this a nonpolar bond, because there is a small difference in electronegativity values, the electrons are still pulled a little bit more toward the iodine, just not enough for us to classify it as polar. Whereas if we look at HCl, hydrogen still a 2.1 electronegativity value, chlorine 3.0. So we would call this a polar bond, and we would also draw the arrow that's illustrating the electronegativity difference and thus the polarity. So there's two notations here. I'm showing you this notation where when we draw this arrow, where the arrowhead is pointing is saying that this atom has a partial negative. And see how we have like a little positive charge at the tail of the arrow? That's saying that that part has a partial positive. And so both of these notations can be helpful. And so what you'll see is I'll change between the notations to get you used to it, because when you take organic chemistry, you're going to have to be able to do both. So for the sake of time, you can go ahead and stop right now. Or if you want to do a couple of practice with me on this top row, you're welcome to stick around and do 1 or 2 more minutes of practice. So what I want to do is decide which atom is going to have the negative charge. And so what you might do is pause for a moment and look up some electronegativity values for these atoms. So phosphorus is 2.1, bromine is 2.8, arsenic is 2.0, hydrogen is 2.1. And you're probably like, oh my gosh, do I have to memorize these? How does she know these so fast? Oh, I came prepared today and I have a periodic table in front of me that I'm staring at right now. Because no, you don't have to memorize them. That's ridiculous. Because you know the periodic table that I give you, remember it has the values of electronegativity on it. So you're all set. So now that I've listed out some electronegativity values, let's go ahead. We can classify first as polar or nonpolar. So this difference is greater than 0.5, so polar, less than 0.5, nonpolar. 0.5 on the dot is polar. A 0 electronegativity difference, absolutely nonpolar. So even the ones that are nonpolar, if there is a small difference between the two, you still have a little arrow. And what we're going to see is the arrowhead is always pointing to the atom that has the higher electronegativity value, because that is the one that is pulling the electrons toward itself and having the partial negative charge. So if we look at this final example of F2, we don't draw an arrow there because the electronegativity value for them is the same. So you can finish by practicing